All right, welcome. This is Ralston Valley High School AP Chemistry's lecture series, Chapter 6, Lecture number 3, in which we will be investigating Hess's Law. Let's move forward. So during the course of this lecture, we're going to be talking about how to calculate changes in enthalpy for a chemical pathway when direct measurement of the enthalpy change using calorimetry is not feasible. The tool which we're going to be using is referred to as Hess's Law. And Hess's law makes use of the fact that enthalpy itself is a state function. That is to say, it is path independent. All that matters is the current state of the system. It doesn't matter how you got there. Recall we introduced this idea a little bit earlier in our discussions of thermochemistry by talking about energy as a state function, in particular when we talked about changes in potential energy due to elevation. Now, recall that if you have a system where you're trying to travel from point A to point B over the course of a series of mountain pathways, the change in elevation that you'll experience doesn't matter what pathway you take. That is to say, you could go up and over all the summits of the mountains and hike along the ridge, or alternatively, you could dig a tunnel straight from point A to point B, and the overall change in elevation you would experience would be independent of which of those two paths you decided to take. Now, in this manner, enthalpy behaves in a very similar fashion. That is to say, if you wanted to determine the overall enthalpy change for a reaction, you would get the same enthalpy change as if you added up a series of individual reaction steps that added to the same overall net reaction which is occurring. And that's really what we're talking about when we discuss Hess's law. That is, the overall change in enthalpy of a process can be calculated as equivalent to the sum of the changes of the enthalpy of individual steps, as long as the sum of those individual steps yields the overall reaction which you're looking for. And that's kind of the big idea. Now, there are some conventions we're going to apply when following Hess's law. First and foremost, if a chemical reaction is reversed, that would also imply that the mathematical sign of that enthalpy change would also have to be reversed as well. And we can see why that would be true by looking at a quick reaction profile graph. If you have a look at the graph which we've sketched right here, you'll notice that the enthalpy change for this process is negative. That is to say, in the forward direction, this is an exothermic process. But were I to reverse that process, what had been my products would then become my reactants. And you'll notice that the difference in enthalpy from the reactants to the products is the same as in the forward direction for the reverse reaction, only it is an endothermic process with a positive delta H value in the reverse direction. So if for some reason you need to reverse a chemical process, that would imply also an enthalpy change would have to have its sign reversed as well. And a second convention we follow when following Hess's law is that if the reaction is going to be multiplied by some common factor, then the enthalpy change would also be multiplied by the same common factor. And this should make perfect logical sense if you consider for a moment the energy change associated with lifting a box from the floor to table height. Recognize that in order to lift that box, you have to do work. And clearly, if you were to lift the box 3 times from the floor to the table height, you would have to do 3 times as much work. The same idea is true within a chemical system. Suppose for a chemical reaction in which species A reacts to form species B, let's say that the enthalpy change of this reaction was 100 kilojoules per mole of reaction. If we were to run that reaction 3 moles of times, it would logically make sense then that 3 times the amount of energy would be required for that reaction to proceed. That is, 3 times the 100 kilojoules per mole of reaction. So those two conventions are really the key ideas which are going to allow us to apply Hess's law to determine enthalpy changes within chemical systems when direct measurement of the enthalpy change using calorimetry is not feasible. Let's move on to our next slide. So in this next example slide here, we're going to have a look at a perfect example of why Hess's law is useful for us in terms of making calculations of enthalpy changes during chemical reactions when direct measurement of the enthalpy change is impossible using calorimetry. So on the picture that you'll see here on the right side of our page, we see 2 different structural forms of elemental carbon. Elemental carbon can exist in various different allotropes, which essentially means it's the same element, but they have different arrangements of the crystalline structure of the atoms that make up that element. In particular, two of those arrangements are carbon in the form of diamond, you see here on the left-hand side, and carbon in the form of graphite. Again, both are just solid phase carbon, but the differences in their crystalline structures lead them to have meaningfully different physical and chemical properties. Now, my question that I'm going to pose to you here is this. What would be the enthalpy change associated with the formation of graphite from diamond? That is to say, carbon in diamond form changes into carbon in graphite form. And clearly here, this is a place where calorimetry will do me no good. That is to say, I could not simply place a piece of diamond underneath a coffee cup calorimeter and then wait for that diamond over time to turn into graphite, and as it does so, change the temperature of the water inside the calorimeter. The diamond industry has led you to believe for many, many years that diamonds are forever. They're clearly not forever, but they are for a really, really long time. And the rate over which this reaction occurs is incredibly, incredibly slow, implying therefore direct measurement with calorimetry is essentially impossible. But whereas we cannot use calorimetry to measure this reaction directly, I could make use of the fact that carbon is a combustible material. That is to say, I could take a sample of carbon in the graphite form and then react it to elemental oxygen, that is diatomic O2 in the atmosphere, to produce carbon dioxide via a combustion reaction. And you'll note here, as I write that reaction describing the combustion of carbon in graphite form, that we have been given here the heat of combustion of carbon in graphite form from the information in the problem as negative 394 kilojoules per mole of reaction. Note there that is a large negative heat of reaction because the combustion of carbon is highly exothermic. So I've now written a reaction here for which I could actually measure the enthalpy change directly using calorimetry because combustion is a fast process. Now, likewise, I could also write a combustion reaction describing what would happen when you burn diamond. Now, you may be thinking to yourself that diamonds clearly don't burn, but that's just because you haven't made them want to burn. We can change the circumstances under which the diamond exists to make the combustion process more favorable. Primarily, I could do that by grinding the diamond up into very, very fine dust, which would greatly increase the surface area of that diamond, allowing for a combustion reaction to happen much more effectively. So if I pulverize my diamond into a bunch of diamond dust and then I light it on fire, very much so, diamond will in fact burn. And the reaction that would be describing that combustion process would be carbon in the form of diamond, again plus oxygen, since combustion requires oxygen to run, is again going to form carbon dioxide gas. And you'll note here that the combustion of diamond has been listed with a heat of combustion of negative 396 kilojoules per mole of reaction. So I've got two different reactions here that both describe the combustion of carbon in its various different allotropic forms. Now, I can cleverly manipulate those reactions to get me to the answer I'm looking for to determine the energy change associated with turning diamond into graphite. And how I'm going to do that is as simple as I'm going to take that reaction where I described the combustion of graphite, and I'm going to reverse that process. That is to say, the carbon and the O2, which had been reactants, will now be my products of the reaction, and the product, my CO2, will now become my reactant. By flipping that reaction, I now have the new reaction of CO2 decomposes into carbon in the form of graphite and oxygen gas O2. Now, note, as per the conventions we discussed on the previous slide, if I flip a reaction, I also have to flip the sign on the enthalpy change associated with that reaction. So whereas the combustion process had been an exothermic reaction with a heat of combustion of negative 394 kilojoules per mole, this decomposition reaction would therefore be an endothermic process with a heat of reaction of positive 394 kilojoules per mole. And now that I've flipped that reaction around, here's the clever idea. I'm now going to sum my two reactions together. That is, I will sum the reaction describing the combustion of diamond with the reaction describing the decomposition of carbon dioxide. And as I do so, note that the overall process would now be, from the combustion reaction on the reactant side, carbon in the form of diamond plus O2 gas, and then also on the reactant side would be from my decomposition, the species carbon dioxide gas, CO2, Then on the product side, I would have, from the combustion reaction, the species carbon dioxide, CO2, and then the two products from the decomposition, which would be carbon in the form of graphite, plus our oxygen gas, O2. And note here that I've got several species that show up both on the reactants and the product side, implying, therefore, I can cancel those species out. As I do so, I will cancel out both the oxygen, the O2, as well as the carbon dioxide, CO2, leaving me with the net sum reaction describing carbon in the form of diamond turning into carbon in the form of graphite. And as we discussed on our previous slide, the sum of the individual enthalpy changes of the steps of the reaction should equal the overall enthalpy change associated with the reaction as a whole. So I can simply add together then the enthalpy change of negative 396 kilojoules per mole from the combustion of the diamond, plus the positive 394 kilojoules per mole from the decomposition of the carbon dioxide gas, yielding an overall enthalpy change of minus 2 kilojoules per mole of reaction for turning diamond into graphite. And note what that really means here is that the diamond industry has been lying to you. That is to say, from a thermodynamic standpoint, graphite exists at a lower potential energy than diamond, as the process of turning diamond into graphite is itself an exothermic process. And because, as we've seen, things in nature tend to trend towards lower states of potential energy, that would imply, therefore, that diamonds are not really forever. They're just for a very, very long time. Graphite is the one that's forever. All right, so there's an example problem. We'll look on to our next slides. All right, so we saw on our previous slide here that some reactions are able to have their enthalpy changes calculated when using Hess's law when direct measurement with calorimetry is not possible. On this slide, we're going to describe a process by which we can apply the same conceptual idea using a concept we refer to as the standard enthalpy of formation. This is kind of like Hess's law taken to its extreme. By definition, a standard enthalpy of formation is the change in enthalpy of a system that accompanies the formation of 1 mole of a chemical species from its elements in their standard states. Now, note here that by this definition, the enthalpy of formation of an element must be, by definition, then a value of 0 kilojoules per mole. Because again, if we're looking at forming an element in its standard state out of the element in its standard state, that means forming an element out of itself, which clearly at that point would have no associated change in the energy of the system. So for this reason, whenever you look up standard enthalpy of formation data in your book for an elemental species in their standard states, those values are always 0. Now, note here, importantly, that by definition, a standard state is going to be defined as follows. Number 1, for gas phase species, gases must exist in their standard state if the partial pressure of that gas is a pressure of 1 atmosphere pressure. For aqueous solutions to be in their standard state, by definition, they must have a concentration of 1 molar. And note importantly here, folks, for elements to be in their standard state, they must be in the form in which that element would exist naturally at a pressure of 1 atmosphere and 25 degrees Celsius, which implies some elements in their standard state might exist as solid phase species, like, say, many metals. Some elements in their standard state might exist as gas phase species, like, say, a lot of those halogens on the right-hand side of your periodic table, or oxygen, nitrogen, or hydrogen. And some elements in their standard states may be, in particular, diatomic species. So make sure to watch out for those halon elements, that is the halogens plus hydrogen, oxygen, and nitrogen, which themselves are diatomic in their standard states. Now, the big idea about how we can apply the idea of standard enthalpy of formation and Hess's law to make calculations of enthalpy changes for reactions is that you could quite feasibly start off with an initial set of reactants and then start off by breaking all of those reactants apart into their component elements in their standard states. There will be an enthalpy change associated with that process of breaking apart all the bonds in the reactant species to form those elements in their standard states. Once you had those elements in their standard states, you could then look at the enthalpy changes associated with forming the products of that reaction by making the bonds in the products. So again, by a comparison of the amount of energy required to break all the bonds in the reactants, in comparison to the amount of energy change associated with making all those bonds out of the elements in their products, you could therefore determine the overall enthalpy change of the reaction, essentially by applying Hess's law. And we'll see how that works on our next slides. So on this next slide, we're going to see here a couple of alternate pathways that will allow us to make a calculation for the overall enthalpy change of a reaction involving the combustion of methane gas. Note here that I've given you at the bottom of this table a reaction describing methane gas being burned in the presence of elemental oxygen, that is diatomic O2, to produce the products carbon dioxide gas, CO2, and water vapor, H2O. And we've given you here a balanced equation describing that combustion reaction. Now, what I would like to do is to determine the overall enthalpy change for this reaction using thermodynamic data which is provided to me in my textbook. That is to say, I'm going to look up the standard enthalpy changes of formation of each of the reactant and product species present in this reaction. You can kind of think about this as like the brute force method of applying Hess's law. So let's go ahead and start off here with my reactant species. On the reactant side of my equation, I know that I'm going to need to have methane gas, that is CH4. So let's go ahead now and write the formation reaction describing the formation of methane gas out of the elements which comprise methane in their standard states. That is to say, if I wanted to make methane CH4 out of elemental carbon, the carbon would have to be in solid phase, so that would be carbon solid. And then the hydrogen that I would be using to make my methane would have to be the diatomic molecule H2 in the gas phase. And because I need 4 hydrogens overall to make methane, that would imply to balance this equation, I would need to have 2 molecules of diatomic H2. So the reaction that would describe the formation of methane gas from their elements in their standard states would be solid carbon plus 2H2 gas forms CH4 gas. And I can look up the standard enthalpy of formation, you might hear this referred to as a heat of formation, in the appendix in the back of my textbook. And as I do so, I find a listed standard enthalpy of formation of negative 75 kilojoules per mole of reaction. And note that for these reactions, it is always by definition per mole of product formed. So I now have a reaction describing the formation of methane gas from its elements in their standard states. The next reactant present in my system is oxygen gas, O2. Now, this one's an incredibly easy one to deal with because if I wanted to write a reaction describing the formation of diatomic oxygen gas from its elements in their standard states, that would be, by definition, the formation of oxygen gas out of oxygen gas. And clearly, because this reaction describes the formation of a product out of that product itself, the enthalpy change associated with this process would be, by definition, 0 kilojoules per mole. That one's easy peasy. Now, looking on the product side, the things that we're producing via this chemical reaction are carbon dioxide and water vapor. Describing here the formation of carbon dioxide from its elements in their standard states would be solid phase carbon plus O2 diatomic oxygen gas reacting to form the product carbon dioxide gas, CO2. And again, I can look up the standard heat of formation for carbon dioxide gas in my textbook. I find that as a value of negative 394 kilojoules per mole of reaction. And last but not least, for my final reaction describing the formation of the product, water vapor, that would be formed out of the elements hydrogen, which again is in standard state diatomic H2 gas, plus, and be careful here, 1/2 mole of O2 gas per mole of water vapor formed. Again, because a formation reaction is always described as forming 1 mole of that product, because 1 mole of water vapor contains 1 mole of oxygen atoms, I would only need 1/2 mole of diatomic O2 molecules to make that 1 mole of water vapor as a product. So my reaction again would be H2 gas plus 1/2 mole of O2 gas forms 1 mole of H2O gas. And I can look up this heat of formation in the back of my textbook, which turns out to be a value of negative 296 kilojoules per mole of reaction. So I now have formation reactions and the associated enthalpy changes of formation for all of the different reactant and product species present. And here's how we're now going to apply Hess's law. I know the overall reaction I want to describe, again, is for the combustion of methane, in which methane and oxygen are the reactants, and carbon dioxide and water vapor are the products. So at this point, just like a little puzzle now, I need to essentially make that reaction out of the 4 individual formation reactions that we have previously written now. So the first step in this process for me would be to take a look at the first reactant, methane CH4. In the overall reaction, that needs to be on the reactant side, but in my formation reactions, I see it here on the product side. So I'm going to take that formation reaction for the formation of methane, and I'm going to reverse that reaction, giving me now CH4 gas decomposes into solid phase carbon and 2 H2 gas molecules. And again, if I reverse a reaction step, I also need to reverse the sign on the enthalpy change of that process. So whereas it had been a negative 75 kilojoules per mole of methane formed, it would therefore be a positive 75 kilojoules per mole of methane which decomposes. So now methane's in the correct location. My oxygen gas already seems to be on the correct side of my reactions here, so I'm going to skip that for the time being. And let's move down to the carbon dioxide, my product. The first product, CO2, needs to show up on the product side of my reaction. It also shows up on the product side of the formation reactions in the third reaction down, describing the heat of formation of carbon dioxide gas. So I'm going to keep that reaction exactly as it is. That CO2 gas is already in the right place. The final step along the way here is to deal with the water vapor. Now, water vapor shows up on the product side of my overall reaction I'm aiming to create here, but I need not just 1 mole of water vapor produced, but 2 moles of water vapor produced. And my formation reaction describing the formation of water only produces 1 mole of water vapor. So for that reason, I'm going to go ahead and I'm going to multiply the entirety of the formation reaction describing the formation of water by the common factor of 2. And as I do that, I now have the formation reaction, which would be 2H2 plus 2 times the 1/2 mole of O2 would give me just 1 mole of O2 gas, reacts to form 2 moles of water vapor as a product. And again, because I multiplied that reaction by a common factor, I would also have to multiply the heat of reaction by the same common factor as well. So my new delta H for the new reaction would be 2 times the negative 286 kilojoules per mole of reaction, which would give me therefore negative 572 kilojoules per mole of reaction by my calculation. So at this point, I now have the correct number of moles of each reactant and product species on the correct sides of the equation. I'm now going to go ahead and sum together my 4 formation reactions. And as I do so, note what's happening. First of all, I note that solid phase carbon is produced via the decomposition of the methane in the first step, but it's also consumed in the combustion of carbon to form carbon dioxide in my third step. So I'm going to cancel out the carbon solid off both sides of my equation. I also note here that the production of 2 moles of hydrogen gas is produced on the product side in the decomposition of methane reaction. And then again, 2 moles of hydrogen gas are consumed in my fourth formation reaction describing the formation of water. So I can now go ahead and cancel out those 2 moles of H2 off both sides as well. And clearly also I can cancel out 1 mole of oxygen gas off of both sides from the formation reaction for O2 gas. And as I do so, what I'm left behind with now is, on my reactant side, methane, CH4 gas, and then 2 moles of oxygen, O2 gas, on the reactant side, forming on the product side, carbon dioxide gas, CO2, and then also 2 moles of H2O on the product side. That is to say, I have the overall reaction I was looking for, which describes the combustion of methane gas. To determine the overall heat of reaction for the combustion of methane, all I would have to do now is sum the heats of reaction for each individual step. So as I do so, I have the positive 75 kilojoules per mole reaction plus 0 kilojoules per mole plus a negative 394 kilojoules per mole of reaction plus a negative 572 kilojoules of mole of reaction for each of those 4 individual stepwise steps of my reaction. And this yields an overall enthalpy change of reaction of negative 891 kilojoules per mole of reaction for the overall process. That is to say, the combustion of methane itself is highly exothermic. Now, note here that that process for determining the overall heat of reaction was actually fairly involved and took a lot of work to get to my final answer. There is, however, a shortcut that I can apply here if I do some logical thinking about what steps I just went through. Have a look at this kind of particle level diagram describing the overall reaction, describing the combustion of methane. If I take my reactants on the left-hand side over here, which again were the methane and the oxygen molecules, on the product side, I'm forming the CO2 gas and the water vapor. And essentially what I've done in the formation reaction steps that I did here was I took those reactant molecules and I broke apart all the bonds within those reactant molecules to break them down into the individual elemental species. That is, for the methane, into carbon and hydrogen. The oxygen, again, was already in its elemental form. Now, note that that step of breaking methane down into elemental carbon and hydrogen is in essence the opposite of a formation reaction for methane. That is, it's essentially decomposing that methane into its elements in their standard states. So therefore, what I've really done here is I've essentially taken the opposite of the heats of formation of all the reactant species and summed them together with the heats of formation of all the product species that are associated with making those new products, that is, the carbon dioxide and the water vapor, out of those elements in their standard states, which we formed by decomposing our reactants. So long story short, it would be mathematically a valid statement to state that the overall heat of reaction would be equivalent to the sum of the heats of formation of all the products minus the sum of the heats of formation of all of the reactants. And you'll notice in following this pathway, I'll end up with the exact same resulting heat of reaction as if I had done it step by step using Hess's law as we showed you in the table above. Let's show this calculation. So for the reaction describing the combustion of methane, again, the overall heat of reaction should be equal to the sum of the heats of formation of the products, which in this case would be the heat of formation of my first product, that was CO2 gas, which again was listed here as negative 394 kilojoules per mole, plus, be careful here, 2 times the heat of formation of water vapor, because again, I'm making not just 1 mole, but 2 moles of water vapor as my product there. That would be 2 times negative 286 kilojoules per mole. So that again is the sum of the heats of formation of all my products. I'm going to subtract from that the sum of the heats of formation of all my reactants, which in this case would be minus the negative 75 kilojoules per mole, describing the heat of formation of my methane, and then plus the other reactant species here, which would be 2 times oxygen's 0 kilojoules per mole for the heat of formation of that elemental oxygen. And as I make this calculation here, you'll notice I get the exact same answer of negative 891 kilojoules per mole of reaction. In essence, what I've done there is just recognize that for the reactants heats of formation, we really need to flip the sign because those reactant species are not being formed, they're being decomposed via this process. And beyond that, we're really just simply applying Hess's law. So there we go. We have a new equation here that will allow me to determine a heat of reaction from thermodynamic data, which we can look up in the backs of our textbook. Let's look on to our final slide. So on our last slide here, we're going to look at one final calculation of an enthalpy change for a reaction. This is for a very exciting reaction in which we're going to take elemental aluminum and react it to ferric oxide, that is Fe2O3, in the solid phase, producing aluminum oxide Al2O3 in solid phase, and then elemental iron Fe. We've given you here a balanced chemical equation describing that process. Now, this reaction, as it turns out, is called the thermite reaction, and we're going to see why this reaction is so interesting from our calculation using thermodynamic data from our textbooks. So let's go ahead here and look up the 4 species involved in the reaction, that is the 2 reactants and the 2 products, and find the associated heats of formation for each of those 4 different species. So starting off with the reactant species aluminum, solid phase. By definition, the enthalpy of formation of solid phase aluminum must be 0 kilojoules per mole because, again, that element already is in its standard state in solid phase. The second reactant here, that is the ferric oxide, Fe2O3. As I look up that standard enthalpy of formation for ferric oxide in the back of my textbook, I find a value of negative 826 kilojoules per mole of ferric oxide formed. So a highly exothermic heat of formation. On the product side here, we have the aluminum oxide, Al2O3. That one has a standard heat of formation given to me out of the textbook as negative 1,676 kilojoules per mole of aluminum oxide formed. That is a very exothermic heat of formation. And then the last species present here, again, is the product elemental iron, which would also have a standard enthalpy of formation by definition of 0 kilojoules per mole, as that is already an element in its standard state. So I have now all of my data out of the back of the textbook for the heats of formation of each individual reactant and product species. Now to determine the overall heat of reaction, I can simply take the sum of the heats of formation of all the products and subtract from that the sum of the heats of formation of all of my reactants, which in this calculation here would yield for me a value of the heats of formation of my products, which again was the negative 1,676 kilojoules per mole of aluminum oxide formed, plus 2 times the heat of formation of my iron, which again was 0. So there now is the sum of the heats of formation of my products. I'm going to subtract from that the sum of the heats of formation of my reactants, which again would be 2 times the heat of formation of my aluminum, which again was 0 by definition, plus the heat of formation of my ferric oxide, Fe2O3, which again was given as a value of negative 826 kilojoules per mole of ferric oxide formed. And as I make that subtraction, that is the sum of the heats of formation of the products minus the reactants, it yields for me here an overall reaction enthalpy change of negative 850 kilojoules per mole of reaction. Now, note here, folks, that this is a tremendously large and negative enthalpy change associated with this process, implying, therefore, the thermite reaction is incredibly exothermic. As it turns out, it is so exothermic that the heat evolved from this reaction is generally sufficient to actually melt the iron which is produced as a product of this reaction. So you end up, instead of with solid phase iron, truly actually with molten iron metal produced as a product via this process. All right, so we've now seen here how you can make a calculation of the overall enthalpy of reaction by making use of the standard heats of formation of the reactants and the products. And that is now it for our Hess's Law lecture. Thanks for listening. We'll see you at the next lecture.